question number 1. These are, by the way, shuffled questions, so they're going to be in different orders than what you got. All right, so we are given 4 unknown samples, given the melting points there and the electrical conductivity. You didn't really need to know the conductivity to answer this question, although you could have connected it to what we did in our lab. But if you look at this, if you look at the names and the structures were drawn on the board for you, we can recognize that these are your ionic compounds, so they're going to have the highest melting points because they have that strong ionic bond attraction. This one, calcium sulfate, has the greater Qs, or the greater charges of cations and anions. So we'll expect that one to have the highest melting point. So that's going to be C, is going to be calcium sulfate, and then the next highest melting point is going to be sodium chloride, which is A. All right, now the other 3, we can use the concept. These are molecular compounds. They're covalent bonds now in there. So now we need to know intermolecular forces. Now again, the structures were drawn on the board for you. So I emphasize the number of hydrogen bond areas that each of these can form. Benzoic acid has 1 area of hydrogen bonding. That's going to be the lowest melting point. That's going to be D. And then sucrose has many more. So that's going to have the slightly higher melting point. So sucrose is going to be B, with a melting point a little bit after benzoic acid. All right, moving on. Electronegativity is an atom's attraction for shared electrons when it's in a molecule, and that increases up and to the right until you get to fluorine, right? And this one is asking which one is the lowest. So your answer is going to be down here, and that's going to be cesium. Our next one, how does calcium obey the octet rule? Octet rule is when an atom wants to have the electron configuration of a noble gas. So calcium can do that. Really, one way is to lose its electrons, because metals. All right, calcium has 2 valence electrons. Is it going to get 6 more? Probably not. It's going to rather lose the 2 electrons to look like argon. All right. Number 4, which is least likely to form a compound? We have a metal and a non-metal that can form an ionic bond. Calcium, chlorine, also metal, non-metal. These can form covalent bonds, and here are your 2 noble gases. So noble gases generally don't form bonds, although the larger ones can. All right, number 5, which one has the highest first ionization energy? First ionization energy is the energy required to remove the first electron from the atom. That would be the electron with the highest energy, or farthest away from the nucleus. So that's going to trend up and to the right. These are going to be harder, or they're going to require more energy to ionize. And down here is those electrons are farthest away. They're the most shielded from what they're attracted to. They're going to be require the least energy. All right, but in this case, the choices are all next to each other. We have carbon, nitrogen, oxygen, fluorine. So fluorine is going to be the answer. So it's going to require more energy to remove fluorine's outer electron than the other choices there. All right, quantum numbers, they describe the behavior of electrons. Okay, so N describes how far away that electron is. L describes the shape of the orbital that electron, the probability cloud, the shape. The magnetic quantum number tells you the orientation of that orbital where the electron can be found, and then the spin quantum number tells you the spin of the electron. So they all describe behaviors of electrons. All right, next one here. Which one will be most similar? Periodic table is organized where elements with similar properties caused by similar valence electrons are all in the same group, also known as family. Right, so group 16, A is the answer. Now, they may not seem similar many times, but they're more similar than elements that are located elsewhere on the periodic table. All right, nitrogen, phosphorus, and arsenic there, all in group 15. They give out 5 valence electrons. 2 in the S and 3 in the P. They all end in NS2 and P3. Right? It's 5. All right, scientists discovered a star, okay, and they conclude that it's made up of mostly hydrogen and potassium. How do they know this? Stars are so far away. Answer is A, because elements produce a unique set of spectral lines, and that's called emission spectrum. We also use what's called absorption spectrum, which is similar in concept, but we didn't get to that in class. You certainly wouldn't. Light travels at the same constant speed through a vacuum, and this is just wrong. Just the opposite of what we're trying to teach you. And density is not going to be used to uniquely identify. How would you get the mass or the volume of something, of a star? I don't know. Maybe you can. All right, net charge. Net charge is the overall charge. Now, calcium has a 2 positive charge. Fluorine has a 1 negative charge. Once it becomes an ion, we can crisscross those numbers and get the formula unit. So there's the formula unit, but this still has a 1 negative charge. This still has a 2 positive charge. Those balance out, and the net charge is 0. All right, third principal energy level, when n is equal to 3, L can have values from 0, 2, and -1. So the 0, 1, and 2, right? The 0 represents s orbitals, 1 represents p orbitals, and 2 represents d orbitals. Now, you probably knew that without having to do this. You just probably memorized that on the third energy level there's s, p's, and d's. Now, how is frequency and wavelength related? They're related by the constant of speed of light. And so wavelength times frequency, the product of those give you a constant. So if one goes up, the other one has to go down in order for this to remain constant. So they're inversely related. You're also given a diagram here. You didn't have to use that. Inversely related. All right, so we have ground state, electron configuration of chlorine. Chlorine is over here. It's number 17. So you know that the electron configuration for chlorine is going to end in 3p1, 3p2, 3p3, 3p4, 3p5. 3p5 it's going to end in. It also has 3s2, giving it the 7 valence electrons in the group 7a of the periodic table. Well, there's 2 choices here. You can't have 8 electrons in a p orbital, so the answer is C. Correct Lewis structure for carbon dioxide. All right, carbon dioxide is CO2. All right, carbon contributes 4 valence electrons. Oxygen contributes 6. There's 2 of them. There's a 16. Let's put carbon in the center. It's less electronegative, surrounded with the 2 oxygens. Give them a bonding pair. That's going to use up 4 of our electrons. We're down to 12. Get the terminal atoms in octet. That's going to use up all 12 of our electrons. The central atom still needs more electrons. It only has 4 right now. It has to get 4 more to achieve the octet. We'll remove a lone pair from each of the terminals and get that double bond going. They are all octet. Now, this one is also a, they all have octets, but if you check out the formal charge is not looking good there. So that's why this is going to be the best answer, because it has the formal charge is all 0. All right, which of these atoms or ions end in the 3s2? Well, the s block is here, so we've gone through there, and then the p block here is here. So this represents 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. The answer is going to be argon. Oh, argon is not a choice. Okay, hold on. So, all right, well, it's definitely not going to be that and that. Now, chlorine is, let me do that again. All right, so chlorine is over here. with 17 valence electrons. If it gains one more electron to become this one negative ion, it will have 18. Therefore, it will have the same electron configuration as argon. All right, little structure for hydrogen cyanide. Hydrogen comes in one valence electrons, carbon has 4, and nitrogen has 5, and that gives us a total of 10. Put carbon in the center, it's less electronegative. And let's connect these with the bonding pair. We're down to 6. Put the octet on the terminal. Hydrogen doesn't want more than what it already has. That's going to use up the remaining 6. Notice the carbon only has 4. It needs 4 more to reach the octet. Let's give 2 from that lone pair and 2 from that lone pair. And it's going to have a triple bond there. And so there's your answer. All right, the VSEPR geometry for NH3, you may have done this so many times. It's, I'll just start from the beginning. All right, that's 5, and then the 3 electrons, 1 from each hydrogen, gives us a total of 8. Let's put nitrogen in the center because hydrogen never goes in the center. Connect them with a bonding pair. That's 2 left. Put them there. Now we got bond angles of 109. This is tetrahedral, the electron density geometry, but only the ones that are connected to atoms contribute to the molecular shape. So this is going to be trigonal pyramidal. All right, hydrogen bonds is when a hydrogen is covalently bonded with a very electronegative small atom such as fluorine, oxygen, or nitrogen. And you've got to have a lone pair to interact with them, which these all do. That one doesn't even have a hydrogen. This one neither does that. This is nonpolar, so answer is C. Number 19, or for me at least, this is the nitrite polyatomic ion. Let's see. Let's do this. Nitrogen has 5 valence electrons. Oxygen has 6. There's 2 of them. Don't forget to add that extra 1 electron. That makes it a negative charge on that molecule. So that is 12 plus another 6 is 18. Let's put nitrogen in the center, surrounded with the 2 oxygens. Put a bonding pair there. That's going to bring us down to 14 total. Remaining electrons. Let me do a little better job. Get the terminal atoms to have an octet. All right, so we're down to 2 valence electrons. Put them on the nitrogen in the center. Nitrogen in the center only has 6 valence electrons. It would like 2 more. Let's move a lone pair from one of the oxygens. Create a double bond. Nothing is wrong with that. It's the correct Lewis structure. All right, manganese, number 25. So that is going to be 1, 2, 3, 4. It's right here. All right, manganese is right there. So to write the ground state electron configuration, we'll go to the previous noble gases, argon, and we're going to go through here, 4s2, 3d5. Now we need to remove 2 electrons to make that a 2 positive cation. We remove from the highest principal quantum number, highest n first. We'll remove both of those, and that is going to be our answer. VSEPR, we're looking for square, planar. Well, can't have a square if you've got less than 4, more or less than 4. You can eliminate those choices because they're not going to give you squares. So let's check out what A looks like. All right, xenon is a noble gas, comes on 8 valence electrons. Fluorine is a halogen's got 7 valence electrons is 4 of them. That's 28 plus 8 is 36 total valence electrons to work with. All right, let's put xenon in the center. Let's put the 4 fluorines around it. Sorry, I already know what this is going to look like, so I'm going to save myself a little bit of time. Let's connect them. 4 bonding pairs. That's 8 we just used, so we are down to the 28. Get the terminal of fluorines and octet by putting 6 more electrons around each of them. That's going to use up 24 more. Yeah, down to 4. All right, so this is going to be your answer. There's your square. That's your planar. You can draw sulfur tetrafluoride, and you'll see that it's there's going to be a lone pair of that. All right, bond angles, CF4, carbon, 4 valence electrons, fluorine 7 times 4, 28, got 32. There's 8 of them. We got 24 left. Put all 24 on these fluorines. All right, anyway, you might recognize right away that carbon already has 8 and can't have an expanded octet because it's in period 2. It's tetrahedral. It's 109.5 degrees. All right, what is wrong with this? All right, even if you didn't know the names of your roles, they're all violated. So you could get this right without even knowing the names. All right, that needs to go there. This electron, that's a violation of Hund's rule. There's nothing there. That was skipped. That's a violation of Aufbau's rule. That thing is violating Pauli's rule. So all the rules are broken. Answer is D. Bond angle on carbon dioxide, we already drew this for you in another multiple choice question, but whether you had a double bond or a single bond and a triple bond, in any case, that bond angle is 180 degrees. It's a linear molecule. All right. Sulfur comes in with 6 valence electrons. Fluorine has 7. There's 4 of them. 28 plus the 6 is 34. Let's put sulfur in the center. Surrounded with the 4 hydrogens. Surrounded with the 4 fluorines. Connect them with the bonding pair. It's going to use up 8. We're down to 26. Putting 6 more on each of the 4 fluorines is going to use up 24, and we're going to be down to 2 more. Put them on the central sulfur. Sulfur can have an expanded octet. Answer C. Which one does not have a single bond? Does not. So nitrogen. So these are both halogens. So they're going to both look the same, and the hydrogen can only have a single bond. So nitrogen is going to look like this, as a triple bond. If you do your lowest structure, that's what you will get. All right, geometry of, let's put iodine, chlorine, 21 plus the 7, 28 valence electrons to work with. Iodine goes in the center, so it's less electronegative. We'll put chlorine on one side, chlorine on another side, and surrounded with the chlorines, let's connect them with the bonding pair. That's going to use up 6 of our valence electrons. We're down to 22. Get the valence electrons on the terminals so they can get the octet. That's going to use up 18 more. We got 4 more left. That's T-shape. But when you remove, you got to remove from the equatorial, remember? So it'll turn seesaw, and then if you remove another one, it'll turn T-shape. Okay, here we go. We have a metal and a non-metal. It's going to be ionic compound transfer of electrons. Magnesium has a 2 positive charge. Fluorine has a 1 negative charge. Crisscross those numbers to get the formula unit. There it is. So you can eliminate A and B. All right, so draw the Lewis structure. Okay, that one goes there, that one goes there, and then you're going to look like that. All right, emitting light. Emitting light frequency is proportional to energy. All right, so it's going to be the biggest jump down. Answer C. B and D are absorbing energy for those electrons to transition to higher energy orbitals. All right, so how are these wavelengths related to each element? It's because the electrons are transitioning. All right, each element, okay, neon in this case, and helium has unique electronic transitions, which produce unique wavelengths and frequencies and colors. What will happen if you introduced another element? That's called a mixture, and that thing only produces ultraviolet light. It doesn't matter because neon's electron configuration, right? Neon, nothing would happen. Same colors, right? Emitted wavelengths would not change because electronic transitions are set, right? Are characteristic to neon and helium, right? So those electronic transitions for neon and helium are not going to change because you add another element. Noble gas for lead is down there. So the previous noble gas is xenon. Start with that. All right, let's go through here. Go through 6s2. Go down here. 4f14. And then go through there. 5d10. And then you end up at 6p1, 6p2. My stylus is struggling at this point. All right, trend going across a period. Sodium is going to be bigger than argon, right? Because going across the shielding remains the same or relatively the same. Shielding relatively unchanged going across a period. Nuclear charge increases. So as you go across the period, left to right, there's more of a nuclear charge pulling the electrons inward, so they get smaller. Nuclear charge increases. That'd be nice if you use both those key terms in your answer. All right, PES. This is your 1s, 2 electrons. This is your 2s, 2 electrons. Right, this is 3 times the height, and you're doing the number, relative number, so that must be 6 electrons. What could that be? Your p orbital holds 6 electrons. This is your 3s2 electrons. This is your 3p6 electrons. Okay. Mendeleev organized his periodic table of mass and then grouped them by properties. That's what we did in our very first phenomena activity, or whatever you want to call it, before we started chapter on the periodic table. All right, so this is out of order. It should be there, but he insisted on putting it in that spot because he grouped them by similar properties. All right. Yeah.